Let's talk about the unit circle. The unit circle is just a circle centered at the origin with a radius of 1. And so there's a crude drawing of it, assuming radius is 1. And angles are defined from the positive x-axis. So positive angles go this way, counterclockwise. Negative angles go the other way. And so demonstrated by my finger just then, and also by this. If my angle is going counterclockwise, it's a positive angle. Clockwise, it's a negative angle. If we express any point on the circle as the point xy, then x squared plus y squared equals 1, and that would be the equation of the circle itself. Just so you know, the generic equation of a circle is this, where xc and yc is the center with a radius of r. And in this particular case, since my center is at the origin, that's 0, and my radius is 1, because it is a unit circle. Now, mathematicians also have defined quadrants here. So this is known as the first, second, third, and fourth quadrant. Again, going counterclockwise, quadrants 1, 2, 3, and 4. This point xy is also defined as the cosine of theta and the sine of theta, where theta is the angle from the positive x-axis to wherever you're drawing that line. So for a first quadrant angle, since x and y are both positive, cosine and sine are both positive. In the second quadrant, we have negative cosine, positive sine, because we have negative x and positive y. Here, they're both negative, so third quadrant, cosine and sine are both negative. And in the fourth quadrant, x is positive, y is negative, or cosine is positive, sine is negative. Another advantage of this, of thinking about the unit circle in terms of trig functions, is the fact that the maximum value of x here is 1, the minimum is negative 1, the maximum of y is 1, the minimum is negative 1, and that is also the same range for cosine and sine. If we take a look at a circle here, and then I've just drawn some angle theta, just for the sake of this demonstration, I am considering this to be a first quadrant angle here, but it actually works no matter what angle we are picking. So I've drawn my line here where r is the distance from this point to that point, and that radius is 1. And then I've drawn this line right here. This is tangent to the curve at that point. And then I've also defined the various trig functions in terms of distances in here. Let's take a little bit of time just exploring that, and we will come back to this. So a cruder sketch of it, and I've defined a couple of the variables here. First, x and y, it's an ordered pair at point x, point y. This is radius of r, which is equal to 1. And x squared plus y squared equals 1 squared. In essence, in my drawing right here, there's 3 different similar triangles. And similar triangles are triangles which have the same angle. So we have triangle CQP. So I'm going from the vertex associated with the angle theta to the vertex associated with the right angle to the vertex associated with the complement of theta, which I label as theta prime. So we have CQP, CPT. So this would be my theta prime down here. This would be my theta prime right here. And we have UPC. So drawing them out with my additional variables, we have these are the 3 triangles where, again, the first letter is associated with angle theta, the second angle is associated with the right angle, and the third angle is associated with the complement of theta. Now with similar triangles, then sides are proportional, so x is to r as y is to l as r is to k. Also, a couple other definitions here. The cosine of theta is x over r, which is just x. Sine of theta is y over r, which is y. And tangent of theta is y over x. For those who used to SOHCAHTOA, the cosine of theta is the adjacent over the hypotenuse. The sine of theta is the opposite over the hypotenuse. And the tangent of theta is the opposite over the adjacent. Basically what I have written here. The difference is that r is 1, and so I first used the letter r here, and then I let r equal 1. Now looking at the similar triangles, if I compare these two right here, that x is to r as the hypotenuse is to hypotenuse, so r is to k. Just working it out, letting r equal 1, we reduce to this. And so k is equal to 1 over x, which is 1 over the cosine of theta, which is secant of theta. So the distance from here to here, where this tangent line hits the x-axis, from here to here, that is the secant of theta. If we look at triangles 1 and 3, they are similar. So x is to n as y is to r. And Working that out, we see that n must be equal to x over y, which is 1 over the tangent of theta, which is cotangent of theta. So n, the distance from here to here, is the cotangent of the angle. Looking at triangles 1 and 3 again, we have r is to m, comparing hypotenuses, is equal to y over r. Working through that, we have y must be equal to 1 over m, or m is 1 over y, which is 1 over the sine of theta, which is the cosecant of theta. So the distance from here to here, where the tangent line hits the y-axis, is the cosecant of theta. And then comparing triangles 1 and 2, x is to r as y is to l. And solving for l, making r equal to 1, we have l as y over x, which is tangent of theta. So that distance is tangent of theta. So if we bring back the previous diagram, where I've actually labeled out, instead of variables, I've labeled out the trig functions here. And then I went about actually measuring it. So I first set up a scale. So my radius is 1, but it's using a vernier caliper. I came up with 57.45 millimeters from here to here. And then I measured each of the distances with a vernier caliper. So in the drawing, these are the actual measurements for each of the lengths. So cosine of theta, this distance from here to here, I measured it as 28.45 millimeters, and then using that scale, translated it into a value, 0.49521. The calculator value, or the correct value, is 0.5 exactly, and so I am off by under 1%, just doing the straight up measurements. Sine of theta is that distance from there to there. In other words, the y value is talked about in reference to the other pages. So I measured it to be 49.35 millimeters, which translates to that value. That's their actual value. My percent error is even less. And then I went through each of these different lengths, and I did the measurement, translated into the actual value using this scale right here, and compared it to the calculator value. My largest off on this was my cosecant of theta, and I was 1.11% off. But anyway, that's the power of the unit circle. The fact that we can find values of trig functions if we have the angle and proper measurements, we can get very close to the actual trig value. And even though I know that most people have calculators nowadays, there is an alternate way of doing it, and it does actually connect to the geometry.